Hi, in this video I will talk about composite quadratures. The idea behind composite quadratures is to divide the interval a and b into m subintervals. So basically this integral can be written as the sum of the integrals in m subintervals. Okay, so in each subinterval we can apply a numerical quadrature such as Newton codes and or Gauss with n plus 1 points in each subinterval. So here you see that here we have an interval, and we can divide this interval with n plus 1 points and then apply a numerical quadrature in each subinterval. So basically we have 1 to m subintervals, and then we can apply numerical quadrature to these subintervals. Here is an example of composite quadratures, and here we use trapezoidal rule for each subinterval. So here we consider that we have m subintervals, and in this graph basically we want to integrate this function, and we divide this interval between 0 to 5 with basically 4 intervals, I1, 2, 3 and 4, and in each subinterval we apply the trapezoidal rule, basically considering 2 points for this interval, and then for the subsequent intervals also we use 2 points. So you see that finally we have basically 5 points for the integration using composite quadratures. Using the trapezoidal rule and composite quadratures, basically we can come up with a formula. So again, we write our integral based on the sum of the integrals over m subintervals. And since we are using trapezoidal rule, basically we are considering 2 points, okay? fxi and fxi minus 1 with the h over 2 weights. And basically the error is the same as before we defined for trapezoidal rule. Here the difference is that we have index of I because we are summing over m intervals. Okay, so finally we come up with this formulation, and you'll see that the difference between the trapezoidal rule and the composite quadratures using trapezoidal rule is that we are just summing over different intervals using the trapezoidal rule. So basically this h, the step size, basically here is the size of the subinterval in the formulation. For equa-space points where we divide our interval between b and a with m equal subintervals, basically the formulation before, the sum formulation before, can be written in a simpler form like this, where we have the sum of the first value function and the last value of the function, and sum of the middle points. Okay, and the error term basically can be written like this, and finally can be written based on m, the number of subintervals. Okay, so you see that here if m tends to infinity, basically the error tends to 0 in the condition that the f2, the second derivative of f, is bounded. Another example is to use Simpson's rule for each subinterval. Okay, so here as an example, again we want to integrate this function, and then we divide the interval between 0 and 5 with 2 subintervals, I1 and I2, and in each subinterval we use the Simpson's rule. So basically we consider 3 points, 1, 2 and 3 for each subinterval for the subinterval 1, and then the next subinterval also again 3 points. Okay, and then we do the integration using the Simpson's rule for each subinterval and sum the two integration. We can write a formula for composite quadratures using Simpson's rule. Again, we write our integral as the sum of the integrals over m subintervals. And since we are using Simpson's rule, basically we consider 3 points or weights for each subinterval with the step size of hi. Okay, The error term is the same as we discussed for the Simpson's rule. And if we consider equispace points, basically this step size can be obtained by dividing the length of the interval between B and A by 2m basically steps, because here in each subinterval we have two steps because we are using Simpson's rule. So if we put this h in the formulation, basically this h comes out of the sum, and then finally we will have this formulation for the quadrature and basically the error term that we defined before. The error for the composite quadrature using Simpson's rule can be written in this form. And basically, if we substitute this sum by the average f mu, we can come up with this term. Or equivalently, we can write the error as a function of the interval b minus a. And you see here that in the denominator, we have the m to the power of 4. So it is obvious that if the number of subintervals is increased, the error tends to 0. Okay, so basically we increase this m and then the error tends to 0. So here we write this as the limit of e when m tends to infinity. This limit becomes 0 in the condition that the derivative term of f is bounded. In this video, I also talk about convergence of quadratures. As the first example, consider that we want to calculate this integral numerically using different quadrature rules. This graph shows the error of different quadrature methods for calculating this integral as a function of the points, the number of points in the logarithmic scale. As you can see here, the Gauss-Legendre method has a much better and faster convergence than other methods. Among the other methods, Newton codes shows a faster convergence with respect to the composite methods, to the 4 composite methods that here we present. But as we will see in the next slide, it is not always that the Newton codes method results in a good convergence. This is a summary of truncation error for different quadrature methods, including Newton codes when we choose odd or even number for n, for Gauss-Legendre where we have the quadrature order of 2n plus 1, and also for composite methods including composite trapezoidal, composite Simpson, and composite Gauss-Legendre. This is another example where we want to calculate numerically this integration of the Runge function, and basically you can see the error as a function of the number of points in the logarithmic scale. You see that all the methods, including Gauss-Legendre and composite methods, basically show a similar convergence rate except the Newton codes, when we see that basically the method doesn't converge. So after some points, basically the error starts to increase, which is a sign of the fact that basically we cannot ensure convergence for the Newton codes method. In conclusion, we cannot guarantee convergence for simple Newton codes quadratures for equispace points and when we increasing the number of points. You observed this in the previous example. We also can guarantee convergence for simple Gauss quadratures by increasing the number of points, and also for composite quadratures when we increase the number of intervals m. The final note on the topic of quadratures is on double integration. So consider this double integration in this form. Basically, the numerical double integration is analogous to analytical double integration. So in other words, to calculate numerically double integration, we first need to integrate with respect to x, calculate the first integration, and then integrate with respect to y and calculate the integration with respect to y. So here is a classwork activity for you, and then I will ask your solutions during the class. Basically, you need to compute this double integral exactly. So this is a double integral. In the integrand is a polynomial, as you can see here, with respect to x and y, and you need to compute this integral using the optimal number of Gauss points in each direction, x and y.